Welcome to the Ash Cloud. I'm Ash Sweeting. Over the last century, our food systems have become increasingly reliant on synthetic nitrogen. This nitrogen fertilizer is mostly made through the energy-intensive haber-bosch process in centralized production plants, often located in politically sensitive locations. These plants have a carbon footprint multiple times greater than the aviation industry. Today we are joined by Frere Byrne of PlasmaLeap, who is developing low-cost mobile technology to synthesize zero-emissions ammonia from air and water. I caught up with Frere to discuss the impact of locally produced nitrogen that is not reliant on fossil fuels and long and centralized supply chains. Frere, thank you very much for joining me today.
Thank you for having me.
So, PlasmaLeap, you recently won the first prize at the Thrive Summit in San Diego, and it's a new technology that can do quite amazing things that I'll let you explain. So let's tell me more about it, what it does, and where the idea came from.
Yeah, thank you. It was a huge honor to kind of even just represent an SPG in Santa Clara, and even more so to kind of take the top spot. In you know, the crux of it, PlasmaLeap is a climate tech company. We exist in the chemical sector, and we build some of the world's most advanced electricity-driven chemical reactors, tackling chemical synthesis in typically high-emitting industries. So we focus mostly on agriculture, mining, and power fuel. And what we build is an electricity-driven reactor that takes any input gas, uses electricity to break that gas down to its building blocks, and allows us to make other chemicals in a really energy efficient way. And so what we're able to do is tackle production of chemicals in sectors that are typically driven by fossil fuels. Really, really exciting space for us, because it's, in essence, a market that hasn't been tackled yet, and it allows us to make zero emissions modular chemical plants that can go on everything from farms to mines to industrial sites that make chemicals, even sites that use huge amounts of fossil fuels. So very, very exciting position for us to be in. We're a 5-year-old company, originally started as a research technology business, and then over the course of 3 to 4 years, through a huge amount of partner research, found ourselves into a number of these high-value applications. And so what PlasmaLeap does now is we focus on chemical reactors at scale that produce two groups of chemicals. So nitrogen chemicals for agriculture and mining, and then hydrocarbon fuels for all kinds of heavy industry.
Wow, and this is low energy production of these fuels. So let's just go into the nitrogen side of things first. When the haber-bosch process kind of was invented, I guess, around the time of the First World War. All that nitrogen originally went into munitions for the First World War, and then these factories were built, and then after that, that nitrogen went into nitrogen fertilizer, which basically led to the whole green revolution. It led to the farming systems that we have today that can produce enough food to feed the world's population. But that's a hugely energy intensive process. And I guess also from the geopolitical side of things, a lot frequently those plants are in countries with lots of oil, such as Russia and places like that. So they also give certain power and to those countries over the customers, which are many parts of the global south as well as the global north. So that's a hugely important. Our societies rely on that nitrogen. So where do you fit into that whole story?
Yeah, I mean, it's a good point you raise. I think the history of the emergence of the haber-bosch is an interesting one relating to us, because we often talk about what we do as very new and novel, and certainly around the turn of the 20th century, as the world's guano markets were dying, there was a very brief period where the type of technology that we use took off. So there's a process called the Birkeland process, which was also ironically run by electricity, not fossil fuels, and produced a bulk of the world's nitrogen for the ag sector in that brief window, that 15 to 20-year window before the haber-bosch really took off. Um, and there are really cool examples of this type of technology being deployed. The hydroelectric facility at Niagara Falls, for example, was a massive nitric acid fertilizer facility. And so during that, in that 20-year period, about 15 to 20% of the world's total nitrogen for agriculture came out of a very similar process to what we produce. But as you kind of rightly called out, as they often do, wars come to an end. And certainly the drivers behind, some of the drivers that exist behind decarbing fossil fuel industries weren't the kind of didn't present the same kind of pressures that they do now, and natural gas was abundant, and so naturally the haber-bosch took off. The problem we have today is that the haber-bosch plants around the world are highly centralized, often, as you say, kind of in politically tempestuous environments, but provide critical chemicals into many of the world's supply chains, not just agriculture, mining, pharmaceuticals, heavy industrial chemicals. But from an agriculture perspective, the ammonia that comes off those plants is responsible for feeding anywhere from between 40 and 60% of the world's population as a critical input crop production. And there are incredible graphs that you see from the FAO and the IFA and many different organizations that show just how ammonia has enabled the mass population growth we've had over the last 100 years. But it's dirty, like it's super dirty. The haber-bosch is 100 years old. And if you look at the emissions from making ammonia from the haber-bosch, they're anywhere from 2 to 3% of global CO2, moving it as high as 1% of CO2 from these large centralized plants, and then using it in agriculture, depending on the estimate, and what data source you follow, is anywhere as from 4 to 6% of global CO2 from emissions at the crop. And so these are massive stacking emissions, often multiples of the aviation sector when you kind of benchmark them. And where we get to very quickly when we talk about this space is without green synthesis processes for ammonia and really good alternative chemicals, the world won't hit net zero. It presents a climate risk. It in many cases presents a sovereignty risk around food supply, because as again, we're talking about a number of highly centralized but very tenuous trade routes from countries that are often sanctioned. And ultimately it presents a huge economic risk because the inputs are incredibly volatile, and the prices that they present are incredibly volatile to the market. And so where we fit in is we present a technology that allows us to detach itself from commodity sectors like natural gas, rely for input, and to peg the input costs to known stable inputs. So in this case, levelized costs of electricity that come off wholesale renewable assets like solar panels and wind turbines, and then present a product into the market that can be deployed at the endpoint of consumption. So it's decentralized and not dependent on international trade routes, and ultimately is highly efficient. So it ends up with very cheap product.
So am I correct to understand that from that ag perspective? Firstly, you said you needed gas as an input and nitrogen, the atmosphere is something like 80 odd percent nitrogen, if I'm correct. So there's an abundant source of nitrogen. It's just a matter of taking it from the air and turning into the not just, but it's there if you know how to take it from the air and transform it into a usable form for growing crops and food. And this is a portable, self-contained solar regeneratively powered unit that would be deployable on a big cropping farm, say in the US or in Australia or in Latin America, potentially, or also it could be in a village somewhere in Africa or in Asia where you'd be providing smaller amounts of fertilizer to the local farmers. Based on renewable, so you're disconnecting that link to the global fertilizer supply chain and the geopolitical risks of that. You're taking away the energy needed to produce that fertilizer, and you're giving much more, I guess, local resilience and potentially food security to these local communities because they're not so exposed to all those geopolitical and economic winds.
Yeah, totally. I mean, I think the great irony is, the where you look at the interest that we have for our technology, and it's all driven by the same types of market drivers. But if you look at a small sub-Saharan African farm that is anywhere from kind of 1 to 10 hectares, but on average around 1 hectare, um, and often those types of farms are a split of subsistence and small scale commercial farming. And then you look at a cereal cropper on the east coast in Australia, we all have farms that are 10,000 hectares, in some cases up to 400, 500,000 hectares. You get massive farms. Generally, the problems that those farmers are faced with are very similar. They're no matter, and that is with very different purchasing power in the economic operations of those farms. They're like exposed to hugely volatile price inputs. Supply chain is incredibly intermittent, and often those two things are linked. And then there's little control around what product actually turns up in the port and gets to the farm. Um, it's a fascinating problem because it doesn't distinguish between the rich and the poor. Is the way I like to think about it. And we can solve the challenges with the technology that we produce, for all of those sectors or segments, however you want to put it, with a modular chemical plant. Um, it's an interesting position to be in because we're hitting the trifecta of climate, supply chain, and ultimately price and input security.
So as that's fascinating what you said about the sub-Saharan African farmer and the Australian broadacre cropping farmer. But if we take a step back from your business's perspective, and delivering the unit to those different markets, there's a plethora of different challenges that are not as similar as their decision-making process. So how do you address that? Obviously you've got the need to scale, grow revenue, get the technology in the market, work through whatever regulatory or approval processes. Um, and then scale that across different geographies to have this technology providing the benefits that it can. So how do you approach that?
Yeah, it's a good point. I mean, you're right. The customer problems might be the same. The market is very different from sub-Saharan Africa to Australia. Certainly, the regulatory environment is very different. Um, Ironically, the stuff that goes onto our food in Australia is typically not regulated. So the fertilizer market is not a regulated market in Australia. It certainly is in terms of labeling standards and things like that, but mostly from a safety perspective. Um, where it gets a little bit hairier is often the chemicals that we use to feed our plants are also the chemicals we use to blow things out of the ground and make bombs and all types of things like that. So that's where you start to get heavier regulation and more controls in the market. Um, but to kind of step back to the crux of what I think you're asking is, um, the biggest problems in the market at the moment as they exist, as certainly as we see it, are mostly related to supply chain, and that's if you look at price volatility and supply intermittency, all of those are in some way, shape, or form a factor of global supply chains and turbulent geopolitics. Um, and so there are there are a number of themes, and there's many different technology companies around the world chasing the same mecca that we chase, which is distributed green chemical production. The two big drivers of that, and they're largely not too dependent on the regulatory structures or the ability to distribute the technology. The ability to get your technology to the endpoint of consumption, so the ability to actually decentralize the technology, and that could mean, in the case of agriculture, it could mean on the farm, but more often we talk about decentralized tech as regional hubs that might do whole regions, and there is a degree of, and forgive the kind of cliche of this term, but last mile distribution. Um, so that's a huge factor, and then the other one is access to cheap renewable power. In order to decarb tech, but in most cases actually provide the key ingredient to be able to produce these chemicals. Like they're the things that enable the ability to get these types of new technologies out into the market. Um, unlike unlike your traditional supply chains, um, there is a lot less reliance on safe and stable trade routes, lack of war, lack of international war with key input producers. And so it becomes a very kind of stable market to play into. Um, and so for us, it's an interesting one, because I think you're able to kill many birds with one stone, so to speak. I think the question is, at the moment, there are many different technologies that are trying to do trying to do the same thing in many different markets. Actually, this is not just a nitrogen problem; it's a hydrocarbons problem. You see it in a range of different, industrial B2B chemicals. And so it will be interesting to see what technologies win and why.
That's really interesting. 20 odd years ago, I managed a seed fertilizer distribution project across 7 or 8 provinces in southern Afghanistan, where we had to get it was only a bag of fertilizer per farmer, but we distributed these bags of fertilizer to 120,000 farmers across all these provinces. And this was kind of when the war was kicking off, and the logistics of getting them there through whatever checkpoints, whoever controlled those checkpoints, and dealing with whatever palms needed to be greased to do that. The managing of it was all distributed through the local departments of agriculture, the provincial departments of agriculture, and let's just say the corruption and graft that went on in that space, and that there was no shortages of challenges to, and then which farmers were selected to participate compared to which ones weren't. Um, so having ways to get and obviously this is a place where food security is not food is not secure. Um, and having a way for these farmers to be able to produce better and more food would be have huge implications, and all those, I guess, political issues aren't one-offs. They all have repercussions that undermine society and trust in governance and all sorts of things like that. So, it's a very big issue, and having other solutions is hugely valuable.
Yeah, yeah. I'm sorry, and you prompted something that I forgot about a moment ago. Like that, electrification is one big theme, decentralization is the other big theme. It's not just about the big supply chains, though. It's about all the intermediaries, and as you put it, kind of greasy palms that feed into the process. And so the ability to deploy technology that's static, at the end point, um, theoretically should bypass a lot of those intermediaries, at least after it's been deployed.
Yeah, one off. In
Why
terms
not?
of in terms of what it looks like and how it operates, do you need what levels of education and technical capability do you need to operate it? What sort of education systems or training systems need to come with it, and how big is it? What does it look like?
Well, maybe I'll step back, because I kind of gave a bit of a foray into the technology and how it works. But just to give a little bit more detail. So for the listeners, what we've developed is a zero emissions modular chemical plant that produces industrial grade nitrates and ammonia from air, water, and renewable electricities. So we cut fossil fuels out of the process, cut hydrogen out of the process, which many people have heard of when it comes to green haber-bosch and green ammonia production, and end up with a process that's completely emissions free. And so we call that modular chemical plant NFix. Um, and in its main form, it's deployed as a single 40-foot containerized unit on a farm, or those 40-foot units can be racked like batteries to gigaton scale plants for the manufacturing and production of regional hub facilities. However, we have also got a number of use case applications where we downscale those units to meet the need of the use case in the field. So, for example, we also scaled down those units for direct integration into protected cropping, like greenhouses and things like that, at a client scale. And then recently, we've just taken a grant from the Gates Foundation, which you'll be able to read about on their website, where we have actually recently built our first version of a very, very small scale unit, which goes on a sub-Saharan African farm, on a subsistence farm, and provides just the amount of nitrogen required for that family's crop. And so that's probably akin, Ash, to the Afghan, bag of fertilizer per farm scale that you talk about. The idea there being that we want to be able to produce nitrogen at the farm using solar and rainwater harvesting below the lowest commodity prices ever for urea, in the last 20, 30 years. And we have a hypothesis that that is a very achievable thing for us to do with our tech. So we're about to start testing that in the next couple
if
of
you're
months.
building something with that scale and targeted at sub-Saharan African farmers, and I imagine to use it is something that you don't need to
Got to
have
be pretty user
a,
friendly.
a
Yeah.
PhD in chemical engineering to do.
That's correct. I mean, ultimately, our plants are operatorless. We try and
Oh,
flip the whole model of chemical production. So, rather than big centralized plants, we've got small scale modular plants that rack like batteries. We're using electricity, not fossil fuels. Everything's deployed in a 40-foot container because we don't make anything bigger than a 40-foot container. The idea is you don't spend 15 years building these big chemical plants. When you do them big, you knock them out quickly. And you have components that are plug and play and can be rapidly assembled. But importantly, they're also operatorless. So everything is run with power electronics. Even the very first units that we ran in New South Wales with our first field tests, we ran out of our facilities in Marrickville from our desks eventually. And so, all of the complex stuff that happens in the units is done using algorithms. And then all of the stuff that needs to be done, at the point of consumption in the field is typically your regular behavior and practice. Top up your tanks, apply your chemicals, those types of things. So very little training required. I think one of the things I've seen is, and you've probably seen this a lot, Ash. I know you've looked at a lot of and been involved in lots of different emerging technology, particularly in the ag space. But one of the things that you always hear people say is, all we need to do is train people. And I always think that that's a pretty quick way to make most things not work.
I uh, from my experience working in the places I've worked, it's been very frequently reinforced that the human challenges, social, cultural, etc., perceptions, ideas are generally much more challenging than the technical or the financial ones. That reinforces once again that perception.
Yeah. Well, we have the luxury of having all of those challenges.
That's
So
brilliant though. That's brilliant. The fact that if it doesn't require behavioral change, that's a huge advantage. In terms of
can I grab you there? Actually, there's one point. It doesn't not necessarily require behavioral change. It doesn't require education to use it. I think one of the things that we talk about a lot is, we can make ammonia and we can make ammonium and ultimately many of the products that exist in the market today. But for the emission story that we spoke about, and actually efficiency, um, we encourage using higher value substitutes. So nitric acid is just a water-based nitrate solution, and we turn that into something that is pH neutral. Um, but PlasmaLeap and many of the kind of more cutting edge, I think, emerging thinkers in the market here would generally push this idea that liquid substitutes for ammonia and urea in the ag space are really good for two reasons. They allow often weather independent application and flexibility. And then in the case where you're using nitrate and not urea or ammonia, where a lot of it ends up unfortunately volatilizing into the air or in bulk rainfall events washing away as leachate or runoff, you instead apply chemical forms that are readily absorbed by the plant. So we focus on nitrate solutions that can be applied flexibly in such a way that most of the nitrate ends up in the plant. It ends up being cheaper, more efficient and greener. And so, but it does require some behavioral change because about 60% of the world at the moment spreads and throws solids onto their crops.
Yep.
So we are in the interesting position of, in many cases, getting people to move over from solid fertilizer application in pellets to liquids. It's not hard because the benefits are pretty obvious, but not everything is super frictionless.
No, that all makes sense, and there's no shortage of conversations going on about the overuse of fertilizer from a water pollution, from a nitrous oxide, from just a financial perspective, that the amount that's lost. So we probably don't need to reopen that we don't have need to reopen that can of worms. You mentioned hydrocarbons as well. So when I think of hydrocarbons, I think of fuels like petrol or propane gas or cooking fuels and those sorts of things. And thinking through, the air has got carbon dioxide, so there's carbon there. The air has got hydrogen, so there's hydrogen there. And then that's hydrocarbons, a mixture of those compounds. So what are you doing in that space?
Yeah, I mean, less focused on the air at the moment, just because despite the fact that we've got 400 ppm of CO2, it's not a super rich source of fuel production.
Okay.
I mean, certainly, I'm not making a comment about not needing to deal with the problem. It's just not. It's nothing when you look at you compare the opportunity to point source emissions and things like that.
Okay.
But yeah. So as we discussed, our first focus is providing zero emissions nitric acid in ag and mining. The same reactors that we produce are also capable of synthesizing crude oil, SAFs, methanol from natural gas or biogas. The other thing we can do is make carbon monoxide and hydrogen peroxide from raw point source emissions. Now, the opportunity there is really interesting. You're bang on. It's exactly the type of things that you're talking about, typically hydrocarbon fuels that power heavy goods. That's what we focus on because my view is electrification of those markets for things that need high energy density is, I think that those fuel markets are not going to die. If anything, they'll grow over time. So when we think about markets like the aviation sector where you need high energy dense fuels, like they're not going away anytime soon. And so the beauty of our tech, particularly when you think about things like sustainable aviation fuel, is if instead of taking routes where we're doing things like mixing, bioethanol based fuels with kerosene in order to make them sustainable by name, instead we're able to produce, effectively produce synthetic fuels directly from what would otherwise be fossil fuel type emissions. And so it's a really powerful route for us. I would say it's much earlier stage technology, but it's a really high value application of the reactors, which we are running to ground very quickly.
So on that, from the business perspective, you're going the market, the nitrogen product will be in the market first, and then the hydrocarbon one will follow along at whatever timeframes you're
Yeah,
working
we're
with.
we're
Yeah.
breaking we're breaking ground on our first two regional hubs at the moment, both of which are in Australia, one in New South Wales and one in Tasmania. And I would say it's probably about 24 months for us to get our hydrocarbon fuels, particularly this e-crude product that we make, out of a beaker into something that is an industrial scale pilot.
And it's the same basic technology that's driving both products.
Same same technology. We're driving an electricity through a gas to break it down and reform it into valuable products.
And that's what can you obviously that's a highly commercially important secret and patented and all those sorts of things. So what can you share with us about how that works?
Uh, okay. Um, so I don't want to go too much into plasma. Just for the benefit of the audience, but that process that I mentioned earlier, the Birkeland that ran on Niagara Falls, was a plasma driven chemical process. The problem with that was it was highly energy efficient because it was using heat to heat the bulk of the gas to turn it into plasma in that state where it's highly reactive. Um, we induce an electric field and pass a current through that gas, exciting only the electrons. So we don't have to. It's a much more energy efficient approach, and energy efficiency is the key. Is the key ingredient there. Um, and in order to do that, and this is a bit of a hint as to how you do it, you have to be really precise in how you excite that gas. So you have to create just the right amount of vibrational energy to destabilize the chemical bonds that exist in that gas without creating waste energy in the process, which means you need really precise power electronics, and you need to be able to provide the exact uh, waveform into that gas in order to break it and not waste electricity through the process.
I
And so
imagine.
in order to do that, sorry, Ash, go.
I was just going to imagine, especially with the hydrocarbons, it would be very easy to spend more energy creating the final product than you actually get out of the final product.
I mean, herein lies the great challenge of industry. Not spending more energy to make something than you get you get in the stock that's ready to harvest. You're precise. You're precise. I mean, the way we do it is we hire really good people, that are able to create very very cutting edge power electronics that can do just that. Ironically, nitrogen is harder than hydrocarbons. Like the triple nitrogen bond that
Mhm.
exists in the air is a really hard bond to break. It's why you'll see a lot of companies building electrolyzer technology that generally doesn't make much product, which is a bit sad, but them's the breaks. No, but for us, it's been a multi-year journey getting to this point, and we've had to pull people out of you know TSMC, Space Machines. Our CTO is a guy who developed the power electronics that run the Hadron Collider at CERN. And it's required some pretty smart minds to wrap their head around this problem. It's not and then and it becomes the intersection of complex power electronics and plasma physics, and then you plant agronomy and industrial operations. Uh, it's a bit of a Goldilocks scenario, as you can imagine.
That is wonderful. We're coming up to time, so before we go, is there anything you'd like to add that we haven't already discussed?
Um, Look, I think just for the benefit of the tapes, we are people that are excited about both climate impact, or impact, I should say, from a climate perspective, but also from a poverty perspective when it comes to making the world a better place. I think looking after the environment is one thing. Looking after the people that live in that environment is another. And I think there are many ways to do that. We are one input in a very large supply chain of things required to run the world. Food is just one of them, but it is something that needs to be green, highly accessible, and affordable. Um, and in my opinion, made locally. And we talk a lot about sovereign security. Um, but the systems that I think that have run, uh, fertilizer production for the agricultural market to date are increasingly broken and not providing the not providing the function they should to the whole world. So it's an exciting space for us. I think we're very excited by deep tech with real impact. We generally say that we're one of the few companies building technology with real impact and zero green premium. So certainly anyone in the ag space or the technology space that's interested in that should come and have a chat with us.
Brant, thank you so very, very much for joining me today. It's been an absolute pleasure.
Ash, thank you for having me.
Thank you for listening to the Ash Cloud. Please subscribe to Ash Cloud if you have enjoyed this podcast, where I will continue to discuss food sustainability with guests who bring a deep understanding of the environmental, political and cultural challenges facing our society and creative ideas on how to address them.